Before we finish our discussions on indexing, let's examine a few index structures that have special purposes. They're not directly related to the format of data entries we have discussed before, but it is interesting to know about them in case you hear their name. One of these index structures is an artery. Artery could be used for indexing spatial data. An artery is the n-dimensional extension of B+3. It could be used for indexing of objects spanning regions of space. These objects could be line segments, rectangles, and other polygons. An artery is a balanced tree with indexed objects sorted in leaf nodes, but instead of range of values, the entries are denoted by bounding boxes associated with each tree node. For example, the figure is showing objects with names A, B, C, D to I, and bounding boxes 1, 2, and 3, denoted by the dotted rectangles that contain the objects. The coordinates of the bounding boxes shown as BB1, BB2, and BB3. The bounding box of a leaf node is the smallest rectangle parallel to the axis that contains all objects stored in the leaf node. Another set of special purpose indexes are write-optimized indexes. Performance of random writes could be poor in B+3s as well as in hash indexes. This is due to the number of page loads involved in the random write operations. Two approaches to reduce the cost of writes are log-structured merge trees, or LSM, and buffer trees. An LSM tree consists of several B+3s, starting with a level 0 tree that is in memory. It also has a number of in-disk trees. The lookup operation consists of separate lookups on each of the trees and merging the results. Operations such as insert are performed in the in-memory tree first and written to in-disk trees when in-memory space allocated to tree level 0 is full. That helps in being good for write. A buffer tree is another write-optimized index structure. The main idea behind a buffer tree is associating a buffer with each internal node of a B+3. When a specific buffer becomes full, and that buffer is associated with a specific node, all the entries of a buffer get pushed to disk. Bitmap indexes are also a specialized type of index designed for easy querying on multiple keys. However, each bitmap index is built on a single key. Bitmap indexes work on records that are numbered sequentially. For example, 0 to n. Bitmap is an array of bits, and the bitmap index on attribute A of a relation R includes one bitmap for each value that the attribute can take. For example, the relation shown in the figure has values M and F standing for male and female for attribute gender, and values L1, L2, L3, and L4 for income level. The bitmaps for gender and income level values are shown. Note that each item has one for the bit of the record that has that value. For example, gender F, denoting female, has bit locations 1, 2, and 4 corresponding to those record numbers set to 1. Bitmap indexes are helpful for queries on multiple keys because they can provide an easy means to perform operations such as union and intersection. For example, if we query the sample relation selecting where gender is F and income level is L2, the intersection of bitmap for gender F, which is 01101, and income level L2, which is 01000, provides 01000, which helps in finding a record number 1 satisfying the query easily.